Wrapping up this session, Bastian is going to tell us about a safe GPU systems programming language, which I suspect is going to give us both safety and control, which was set as the target this morning. So yeah, this is fantastic. All right, take it away.
Yeah, thank you. I'm going to present some work that I did together with Michel Steuwer, who is here today, and Sergei Gorlatch. And basically, computing on GPUs is great. We heard today in the keynote that we need to use GPUs if we really want to get the performance out of our system, and we want to do this, and GPUs offer us tons of parallelism, thousands of threads that we can use, and are being used for high-performance programming in many fields now, medical imaging, scientific computing, and of course machine learning, just as some examples. The thing about computing on GPUs is that GPU programming is too hard, at least that's what I'm claiming. And so when we program GPUs, usually we use a programming model like CUDA, for example, which is very low level, inherits a lot of the problems that C and C++ have. Programmers have to manage their threads manually, have to manage memory accesses manually. And this way, it's easy to introduce bugs and, for example, data races. So for example, when you write a CUDA program for the GPU, you write a kernel function. This is a function describing a transposition on a two-dimensional matrix. We read the matrix in and write it out in a transposed form. And this kernel function is executed by thousands of threads. It's pretty much copied onto all the threads, and all the threads run it independently. Threads on the GPU are organized into multi-dimensional blocks. And these blocks are then again organized into a multi-dimensional grid. Then each block and each thread can be indexed or uniquely identified in every dimension. And we can use these indices for explicit indexing to determine where each thread accesses the memory. The problem about this is that when we want to reason about whether this code is correct or whether we have introduced a data race, we kind of need to build up a mental model about the memory we are accessing and the grid that we have currently running this function on. So here, for example, if we write into the temporary array, which we assume is a 4x4 array, and then we assume that our grid is simply a single block of 2x4 threads, then in order to figure out whether our code is correct, we first need to figure out or substitute all the identifiers or the indices in our expression to figure out where each thread accesses the memory. So in this case, for example, the first row of our threads in the block is accessing and writing to a different memory location without a problem. But when we do the same for the second row of our block, then we see that some threads in the second row write into the first row of our array and create a data race, which then leads to undefined behavior, so we have to avoid this. In this case, the problem simply is that we forgot some parentheses. We can reintroduce them, and then every thread is writing to a different memory location, and we don't have a data race anymore. But in a larger program, this kind of bug can be quite hard to find and to debug. So our question is, how can we create a safe GPU programming language? And our answer to that is Descent, a safe GPU systems programming language with a philosophy similar to Rust, that if the program successfully compiles, it should be free of data races and other memory problems. If we look at the same transposed program for the GPU in Descent, the first thing we notice is that the function that describes the transposition is annotated with a grid. And in this case, we have an explicit annotation with a two-dimensional grid of 64 by 64 blocks, and then for each block, 32 by 8 threads. This means in Descent that this entire function is collectively executed by the entire grid. And then within this function, we describe how the entire grid collectively executes the function. So for that, we use the scheduling instruction in line 6, for example, where we say that for each block in the y and the x dimensions, so both dimensions of the grid, we want to schedule some computation. And then in the body of the schedule, we say the same thing again for the threads in the block in this case. So then when we are in the innermost body, where we describe what each thread does, we can use normal instructions for the threads. We can write and read from memory and to memory. For example, in line 14, the threads are accessing and writing into the output array. And here we make sure in this line that each thread has to write into a different memory location. And we do this by using views and by them describing how each thread or which memory locations each thread has access to and which memory locations it owns. So for this example, for this line, for example, we again can assume that our output array is simply a 4x4 array. And we now want to distribute the memory locations that form a tile in our array over all the blocks. So the first thing we do is we apply a view. And this view reshapes our array into a 4-dimensional array consisting of 2 rows. And each row contains 2 tiles. And now we can simply distribute these tiles over all our 2-dimensional block or over our 2-dimensional grid. I'm writing here block 1, 1 to say that the block at index 1 and 1 is accessing the tile in the bottom right corner, but in reality we would write simply block, meaning that all the blocks are going to take ownership over one of the tiles. So here block 1, 1 takes ownership over the tile at index 1 in the row with index 1. And after the block has taken ownership, the block has full access to it. But since we usually want to read and write with threads, we also need to describe within the block the elements that each thread takes ownership over. So we do a similar thing again. We apply another view, group by row. We group the elements together that each thread should own, and then we take ownership with each thread. So here again, for example, the thread with indices 0 and 1 would take the group of elements at index 1 within the row at index 0. Now, the threads have separate access to separate memory locations and are allowed to safely read and write to and from memory. And this is how Descent's extended ownership model ensures that memory is accessed safely via views. In Descent, there exist 5 basic view primitives: map, group, transpose, reverse, and take. And these pretty much only allow us to somehow partition our memory or permute the memory locations so that it's guaranteed to always be safe. And we can then use these basic view primitives to compose more complex views. For example, the group by tile view is simply a composition of a map group followed by a map transpose. And then views are composed to express these kind of complex memory access patterns. Going back to the transpose example in Descent, we now understand that in line 9 here, the threads write safely into the TMP memory because we first group the memory locations and then each thread takes ownership over a different group of memory locations. And then down here in line 15, we also see that, again, each thread now reads safely from each memory location. Or do they? Because in this case, if we type check our program with Descent, we get an error message which says that there's a conflicting memory access. And the reason for that is that in line 9 before, we distributed the ownership of the memory locations in TMP over the threads using the view group by row. But in line 15 now, we are trying to redistribute the ownership using a different view, in this case, a composition of transpose and group by row. Which means that in theory, and in this case it would be the case, different threads would be reading and writing, or possibly reading and writing at the same time, creating a data race again. So the problem here is that after taking the ownership in line 9, we need to release the ownership again to allow renewing or redistributing a new version of the ownership. And we do this by simply introducing a synchronization over the entire block. And this synchronization then for each block releases all the ownerships that threads have taken within the block, so that after this synchronization within the block, each thread can distribute ownership again anew. And this way, Descent ensures that there are no data races. But Descent does a couple more things that we describe in the paper. So we also make sure that we respect the separated memories between CPU and the different GPU memories. The assumptions between CPU and GPU code must match, which we make sure of. Safe memory accesses and branching code must also work, of course. It's quite important for a lot of applications. And then we make sure that there's an absence of barrier divergence, which would also lead to undefined behavior, for example. What we did then is we formalized the type system and we implemented a compiler that translates descent programs into CUDA programs. And we used this compiler to evaluate how performant our approach is. So how easy is it to generate performant CUDA code? And to figure this out, we chose a couple of common benchmarks from different sources with some interesting characteristics that we describe in the paper. Here we show a graph where we show the median relative performance on 2 different GPUs that we measured. And in green we have the CUDA versions, the reference versions, which always have a performance of 1. And then the descent version, if the bar is higher, it's faster, and if it's lower, it's slower. And we see pretty much that programs generated from descent achieve competitive performance to handwritten CUDA. The gem version is kind of an outlier, and the reason for this is that the CUDA version that we are comparing to has done complete loop unrolling on all the loops for the gem, and our generated code generates just loops with static loop bounds, and then we let the CUDA compiler decide, and the CUDA compiler just does a better job at unrolling, and this way our implementation here is faster. But pretty much we are still similarly fast. The same reason goes for Jacobi SVD. One interesting point that I wanted to make is that we can talk about atomic read, modify, write operations, for example, which is why we did the histogram benchmark, for which read, modify, write operations are quite important. And it's nice to see this is very similar to how you use atomic read, modify, write in Rust. And we can simply introduce it here as well. Then additionally, there are still some domains that are quite hard to express. As I have shown, we are pretty much partitioning our data statically, but there are definitely domains where partitioning the data statically is not that easy, especially graph algorithms. So we looked at the single source shortest path graph algorithm, and the implementation we looked at is highly optimized, uses thousands of lines of code, exploits the weak memory model of CUDA, all things that we can currently not express in this way in descent yet. So we introduced simply an unsafe escape hatch, which allows us 2 things. First of all, we can easily interface with external CUDA code, and additionally, sometimes we need to, even in descent itself, we need to access graph data with dynamic indexing, which is again difficult because we don't have the static partitioning anymore. So that means we use the unsafe in this example to implement the algorithm, and then reuse, for example, the existing work list implementation that uses the weak memory model and these kind of things. This way, the unsafe code provides us with a quick method of interfacing with existing CUDA code and integrating more and more CUDA code into descent. To conclude, descent assists programmers in managing CPU and GPU memory and enforcing previously implicit assumptions. Descent extends the concept of ownership to the thread hierarchy and uses views to ensure safe memory accesses on the GPU. And the evaluation shows that descent is expressive enough to write programs that achieve performance on par with handwritten CUDA code. We have created a website, descentlang.org, where you can find a link to the paper, a link to a document with the type system formalization, and a link to the GitHub project with the compiler implementation. Thank you.
Okay, if there's any questions, please feel free to step up to the mic in the center. One thing I was curious about, how is the type system imprecise? Like, are there places where the type system, like what kinds of programs is the type system going to reject that are actually okay?
Yeah, for example, if you have indexing with dynamic indices that you need for graph algorithms, for example, then we don't know into which partition the index wants to go, so we kind of cannot express these kind of programs yet. Yeah.
And I guess maybe the flip side of that, were there any interesting bugs that this caught for you while you were building your evaluation?
You mean
like a favorite mistake that you made that if you'd been writing it in CUDA would have gotten through, but descend kept you safe?
Simply forgetting synchronizations. I mean, barrier synchronizations are easily forgotten. Yeah.
Very nice talk. Thank you very much. How general, or what are the limits of the views that you can compute? Mm-hmm. Are they limited to essentially blocking an array, or you can support something more general like taking the diagonal of blocks of an array?
Ah, interesting.
Because this appears, for example, in an NW and also in LUD, where you descend the computation, so you have a block slice. Mm-hmm. Are you able to support those benchmarks?
Great question. So I think taking like a diagonal is definitely possible. It's a combination of the views and how we select which thread accesses which element. So basically the take can throw away data, and then you would have to do a bit of work to explain how or which data should be thrown away by each thread, like in every row, or which. Actually, we have, sorry, one of the Jacobi SVD, I think, does something in that direction at least. That you take ownership over a row, but you basically need only one memory location from that row. And you can do that with, you distribute the ownership over several threads, and then each thread accesses exactly the element on the diagonal, for example. But they're probably, I'm happy to talk about it further.
Yeah, let's take it offline.
Yeah.
There's time.
So in comparison to descend to the traditional way of writing a CUDA program, you would have your host side code where you would specify essentially the grid dimensions that you encode in your types. And the separation between that and the kernel is so that the kernels are generic-ish over the launch parameters that you would specify. And now I'm wondering, like, two sides of this. One is, since now that you're effectively adding this extra information into the kernels themselves, could you, one, perform other optimizations since you know the entire shapes of these blocks, the dimensions that normally CUDA programs have at runtime only? And second, does this limit the, could you go even further in the type system and say, let's add parameters in certain ways, and like, would that work? How would that limit, would that exacerbate the imprecision problem? Like, could you speculate on that, on both sides of that?
So one, I think so. Currently the translation to CUDA code is very straightforward, but I'm definitely interested into looking into more optimizations, and I definitely think, yes, the extra information should help us in optimizing. Mm-hmm. The second question I didn't fully understand.
Oh, about parameterizing these kernels themselves. Would that be possible? Would that introduce different unforeseen challenges?
You mean parameterizing, for example, the block sizes and these kind of things?
For example,
yes.
Sure.
I think it introduces additional challenges for sure, but I'm very interested in that. I have some ideas on how to approach that already. Yeah.
Sounds great. Thank you.
So what are the reasons you made a new language for this? Can you infer everything from like CUDA code?
You mean can I mean I can already express everything in CUDA. I agree, but yeah, the main reason is that when I write CUDA code, it's very easy to make mistakes, and I want the compiler to help me out and tell me when I made a mistake. That's the reason.
Okay. I'll take it offline.
Okay.
Thank you for the talk.
Thank you.
Did you consider using separation logic to define the semantic of your programming language? Because it doesn't, by skimming your paper, it doesn't look like you did.
Yeah, I mean, not when we started, but by now I'm at the point where I'm thinking, yes, that would be very interesting. Actually, we don't have a formal definition of the semantics yet, so that's definitely a very interesting approach for me to go towards that, yeah. Thank you.
All right, let's thank Bastian and all the speakers from the session one more time.